Good afternoon and welcome to the webinar, Assessing Common Cause for BPS Shared Components. Thank you very much for attending. Just as we get started here, again, a quick reminder, we have muted your microphones, but if you're having any issues with sound, please enable your speakers. And if there's any questions that come up during the webinar, I invite you to use the question tool, which is probably on the right side of your screen, to go ahead and type that question in. I will read them and answer them at the end of the webinar. So let's go ahead and get started. I am Denise Chastain-Knight, your host for this webinar. I am a chemical engineer from Georgia Institute of Technology with 34 years engineering experience in process safety, process improvements, functional safety, and process risk analysis. I've had an opportunity in my career to work in many different and diverse industries. So that's been a really great and enjoyable thing. Let me tell you a little bit about Exida. We are definitely a customer-focused company. We enjoy hearing your feedback. We really very much appreciate it. And the company has grown and in ways in order to serve our customers. We bring experience or expertise that your organization may not have had time or sufficient exposure to develop in-house. And we prepare a lot of tools that help perform related tasks efficiently and in compliance with the standards. We also prepare materials, reference materials. We have published a large number of books and series of books like the supplied, the SERH document. Collectively, there's hundreds of years of experience and thousands of hours of research that has gone into preparing these reference materials. Exida is also known for certification from a product and from a personnel expertise point of view. Exida is accredited to perform certification and works under a strict quality control program. Product certification can be trusted to be complete in full compliance with standards, and personnel certification is competency-based. So folks carrying the CFSE or CFSP have been demonstrated their competence in these areas. We are a global leader in functional safety certification, trusted in the market to deliver certificates that meet requirements of the standards. We're also a leader in the automation cybersecurity certification market. Our understanding of cybersecurity comes with the understanding of an industrial setting and the particular concerns related to cybersecurity attacks. Exida has developed a full lifecycle set of tools. The Silver module, one of the tools within Excelentia, was used in preparation for today's presentation to perform some of the calculation results, and we'll talk a little bit about how we used it as we go through this process. Information comes into a central database with these tools. That means information is captured once, and as it flows through the life cycle and as the process designs, evolves, and operation matures. So that it eliminates the need for duplication of reentry and assures that information that once it has been input is utilized in the same manner downstream. The import and export capability of Excelentia provides for interface between lifecycle management and other operational tools. And in the OEM area, we have two products, ArchX, which is computer system high-level architecture design analysis, and the FMEDA-X is for device failure rate and failure mode prediction for safety and availability analysis. So let's move on to the topics of our webinar. A lot of energy around common cause discussion. So we're going to start by looking at the base definitions, what the standards say, and how they define common cause and common mode failure. We'll talk about some of the sources of common cause or common mode failure that are most frequently seen. Then we'll do a little deeper dive into IEC 61511. What are the requirements throughout the standard, and talk a little bit about those in detail. 61511 requires that common cause be assessed, and it says it can be done either qualitatively or quantitatively. And we're going to do a comparison of those two methods, the pros and cons of the methods. We'll talk a little bit about beta and how beta is calculated, and illustrate what part of common cause failure is covered in beta and what part is not. And then finally, we will do an example problem using a steam turbine control that will illustrate how to calculate quantitatively common cause. So starting with our definitions, common cause failure, this is from IEC 61511, and we have the base definition, concurrent failures of different devices resulting from a single event, where they're not consequences of each other. And there's a number of notes that go with this definition to attempt to clarify it a little bit further. Common cause failures can lead to common mode failures, and they can be more significant than we might think when we start looking at them. Humans have a big impact on the system, external failures. There's a lot of places where common cause can originate from that are ever present. When we look at common mode failures, the difference there is concurrent failures of different devices, but they're characterized by the same failure mode. So we can have multiple causes, different causes, but we fail in the same mode. And that is equally concerning as having a single cause that would fail us in more than one place. A very important point about common cause failures is they do reduce the effect of system redundancy, and we put redundancy in there into a system in order to try and combat this potential and to increase reliability. So what are our sources of common cause failure? They can be either systematic or they can be random, and we can build systematic ones into the design and construction of the components. That's a lot of what we look at for the systematic capability when we're doing verification on the components from vendors. But we can also put systematic errors into our operation and maintenance through our proof testing techniques or our bypass procedures. So we can create these systematic faults either coming with the equipment or outside the equipment in how we manage and use that equipment. Human error is always a concern, and humans can fail in consistent ways or error in doing something in a way that is repetitive that may affect more than one device. And then, of course, there's the ever-present environment, our temperature, our humidity, electrical conditions. I mean, all of these things can lead to failures of devices in a common cause or common mode. Some example of common causes between systems: if we have similar equipment used in the SIS and the BPCS, even if they're in independent loops, they can have common causes for failure or common modes. We can have process issues such as plugging or fouling. Fouling may affect both the BPCS sensor and the SIS sensor. Plugging could affect not only our sensors, but could affect our relief devices. And then one thing we'll look at in a lot of detail today, and the examples that we're looking at, is a case where we have a BPS sensor that could lead to a demand on the SIS, or the variant we're actually going to look at is where there's a final element in the, or control element in the BPCS that leads to a demand on the sensor, and then at the same time it reduces the reliability of the SIF. Where we may have two separate sensors and logic solvers that both call on the same final element. That is often seen. An example would be when we have the large machinery like a turbine, where it has trips that are internal to the safety system of the turbine but we may have sensors in our plant sys that ends up calling on those same final elements to do the trip as what the equipment PLC or safety logic solver would do. Synchronous proof testing. Someone's having a bad day. This is proof testing where we have the same people or things are being proof tested at the same time. So there's the potential to introduce a systematic error in that. Or if we've got tools we're using to do our proof testing that were not properly calibrated, we can introduce some common cause error there by calibrating all of our equipment using a tool that's not in itself calibrated. And of course, we have the different areas where we interact with the SIS and the BPCS where communications occur, or the activity of bypassing. When we look at IEC 61511, it actually addresses common cause in a lot of different places, in many places in the safety life cycle, starting with the hazards and risk assessment. It's mentioned frequently in the allocation of safety functions to protection layers because our goal in that activity is to have safety layers of protections that are independent. IPLs is what we refer to them, and the independent is very critical. If we have a potential failure that can affect more than one of those protection layers, then we've got common cause. So we need to be careful in understanding that in our IPL assessment. If there is common cause identified, it needs to be listed in the safety requirement specification. That is one of the requirements under clause 10.3.2. And then, of course, in the SIS design and engineering, there's a number of references to places where in both the hardware and the software that common cause needs to be addressed. And then there's the proof testing mentioned. I did not list 9.2.6 because it's one of the major ones on how to address the causes within our protection layers. Important language here, let me highlight this with the laser, that we need to make sure that of the independence, there we go, we have the independence shall be assessed. And then it also says that it needs to be sufficiently low compared to the risk reduction requirements. And we're going to hear those words many times during this presentation because, excuse me, our goal in looking at the common cause is to find out whether it is significant or not. And of course, the language that we see right here in this clause is subjective, determining whether the risk of common cause is sufficiently low compared to the risk reduction requirements. There is some subjectivity in figuring that out, and the qualitative method and the quantitative method would approach this maybe a little bit differently. Particularly called out that must be assessed is one of the cases that we're going to look at today, common cause of failure of the SIS, and the cause that is the cause of the demand. And in the examples we'll look at today, we'll have a failure of a shared device between the BPCS and the SIS. So when it fails in a way that is going to cause a demand on the SIF. But then because it is was originally intended as a final element within the safety instrumented function and it's already failed, it actually degrades the reliability within the SIS in order to be able to make the response. Clause 9.3.5, this note 2 was put in, and I pull it up just because a lot of times folks, when they're doing their layer of assessment, they're going to want to say, well, I've got a hot backup controller on my BPCS. Isn't that, can I take credit for that as an independent protection layer? And IEC 61511 in the most recent edition actually added this note to clarify that point, that because there is so much common cause between your hot backup controller and your primary controller, they are effectively clones of each other when they were designed and installed. So there's a huge amount of common cause between those two, and they are considered part of the protection layer, and that is explicitly stated within the standard now. So what are the requirements for preventing common cause and common mode dependent failures? This within the design side, again, we want to ensure the likelihood of common cause and common mode and dependent failures between the two protection layers. Again, we're seeing these words, is sufficiently low in comparison to the overall safety integrity requirements. We have to do the assessment. It is required for this clause if we have the common cause, common mode, or the dependent failure. And specifically, it lists that we need to look for independence between layers, diversity between layers. Do we have physical separation between those layers? And if we have common cause between the protection layers, then we need to do the assessment. It may be either qualitative, except for SIL 4, or quantitative. If you have SIL 4, it is required to be quantitative. So the central message we see when we look at all of these IEC 61511 messages in detail, and the theme that runs through all of them, is that we can have common cause come from many, many sources. We should always seek to eliminate or minimize and eliminate, if possible, through our design process, common cause and common mode of failure. And where it cannot be avoided, it needs to be accounted for, either through quantitative or qualitative analysis. And we must always make sure that it is sufficiently low in comparison to the overall safety integrity requirements. Here's an example that I used for a voting discussion a few weeks ago, but it's an arrangement that is frequently posited as a safety instrumented function solution to increasing risk reduction factor. In this example, the arrangement introduced, the arguments for this solution include space limitations and a lower cost. The arrangement introduces a source of common cause failure that produces a demand on the SIF while simultaneously reducing the SIF effectiveness. So what we have here in this arrangement, explaining it, is we have an FPV that controls sulfuric acid feed to a reactor. If the control of that feed rate is lost, there is a potential to initiate a runaway reaction in the reactor causing high temperature. So the primary function of the FPV is to maintain that control in our BPCS layer of protection. What has been proposed as a solution for the design for the SIF is to include an independent solenoid valve that will trip the FPV by the SIS, and then of course we have an XPV, an on-off valve, that is in the safety instrumented system. And of course the intent for the SIF is on high temperature in the reactor is to stop the flow and bring us to a safe state. But by doing this design, what we've done is we have this flow, the FPV, which is a part of our basic process control, BPCS layer, and we're trying to share it with our safety instrumented system. But we have this failure mode or failure system where if the FPV fails full open, it is actually going to initiate a demand on the SIF while simultaneously reducing the reliability of the SIF. Because if the FPV is failed open, it's not going to close when it's commanded by the SIF. So the question we are going to want to ask is the common cause failure sufficiently low in comparison to the overall safety integrity requirements? I did well, before we do that calculation, let's look at the two different methodologies, quantitative versus qualitative, and what are the pros and cons between the two of them. The issue with qualitative, of course, is it's subjective. We have kind of a subjective goal here for what is sufficiently low enough, but then we have a qualitative method that brings its own subjectivity to it. So the analysis done on 2 different days by 2 different groups may come up with 2 different answers. Our results may vary. I think when we are doing these kinds of analysis, we may assume perfect conditions or not take into account all the variables, such as people being fatigued or imperfect proof testing, things like that. So we may overlook or understate the actual potential for failure. So I think qualitative, we tend to be potentially optimistic. In the quantitative approach, because we're using failure rate data that is coming from proven sources, from databases that have long history behind them, we're using calculation tools that incorporate methods and include the variables that may address imperfections in it. It is an analytical method, so it's very repeatable, and we can work into our procedure a method that is slightly conservative. So for the purpose of this webinar, at this point, I'm going to step away from qualitative approaches, and we're going to focus just on the quantitative ones, or the quantitative approach that exida has developed. So applying that to this situation here, what drove this scenario, of course, is that we started out with a design, as you see on the screen now. But then at some later date in history, we went back, revalidated our PHA, took a look at our SIF and said, you know what, we need to change the SIL target. We've got risk here that's not being managed. What was considered a SIL 1 SIF now needs to become a SIL 2 with a risk reduction factor of 120. Of course, the original design was a SIL 1, which was perfectly achievable with a single XPV at a risk reduction factor of 26 on the original design. So someone proposes a solution to do this quickly by adding that second solenoid that we talked about on the FPV and using the FPV as a redundant final element. If we go in and do a verification on this design and not consider the common cause of that valve failure affecting the degradation of the SIF, then we would say, oh, our new SIF, when we do our verification calculations, can achieve a risk reduction factor of 154. Sounds like we're in good stead. But when we step back and say, wait a minute, we've got this float, the FPV, which it is a source of failure that will both place a demand on the SIF while simultaneously reducing the reliability of the SIF. And per clause 11.2.10, we are required to do an analysis on this. We step back, do that analysis quantitatively, and we find out that the actual risk reduction factor achieved by this design is 107 when we adjust for that common cause. And you will note that that 107 does not meet the SIL target. So this is why we recommend that we don't do this kind of design, that we have, if we need 2 valves in the SIS, that we do 2 valves that are wholly independent of the BPCS flow control. Because the common cause, I would say that the difference there is significant. Even if it did rise up to the point where it could meet the SIL target after the adjustment, I would still be concerned about how much the system is degraded by the failure of either the flow valve or its actuator. So just to repeat, it is not recommended that we use these second solenoids and share the share a valve with the BPCS, because it is a pretty large difference. Moving on forward, let's look at independent versus dependent failure. We were talking about the beta, and we have methods within the Excellentia tool to calculate the beta, but it's typically looking at these independent failures, due to random or systematic causes that could occur simultaneously in multiple components. And an example I might think of that's a good representation of that is we have multiple wires in that go to the transmitters in a sensor group, something that has 2 or 3 transmitters that are voting. If they're all routed through a shared conduit, we have an opportunity for some common failure here, particularly if that conduit was not sealed properly, and maybe we have conditions that could cause corrosion or some other degradation of the wiring systems within the conduit. Now, the wires themselves are going to fail independently based on their individual rate of corrosion. But it is always possible that more than one wire will fail at any given time. Maybe they short across each other. Then we want to go in and look at dependent failures. These are the ones where we may have a single shared cause, or common modes that fail in the same way due to different stimulus. And an example I might think of on the dependent is where we have a forklift truck that actually strikes this conduit with all this wiring in it, and it's going to fail all of the transmitters at the same time. So your beta calculation, when you're doing your SIL verification calculations, it is structured to look at those independent random or systematic failures, but it does not, through its mechanism, take into account these dependent failures, such as sharing a valve between the BPCS and the SIS. Those have to be accounted for separately. But when we do our SIL calculations, we still want to include the beta. So let's look at beta for a moment. It is very well defined in IEC 61508 Part 6 Annex D. There are two methods that are discussed and examples are given. Typically, our beta range, and this is based on the table for the table method, could range between 0.5 and 10%. And you notice from the numbers we did before that there was much more than 10% involved in that one example we looked at before, difference between when we looked at the common cause between systems. Continuing here with the beta, the table method, there's just kind of a short example there. These are the kinds of questions that are asked. There's a number of different sections. This table is several pages long. And basically what we do is you go through, you answer these questions and select which of these questions is more appropriate within a given section and apply the X and Y factors for that question. This is done in several different areas, and then they are tallied up, and you look up, based on your score, a beta range from a table. The other method that's talked about is the binomial failure rate, or known as the shock model, which in the example in IEC 61508, they are using a fault tree in that example. Excellentia uses the table method B1. So I certainly encourage anyone, if you want to know more about the beta, we don't have time within our structure today to go into it in a lot of detail, but if you wish to know more about it, you can certainly refer to IEC 61508 Part 6 Annex D for more information. So moving on to the example, I will show you how to calculate use the quantitative approach to calculate a shared valve between BPCS and the SIS and understand how that common cause is calculated. This method was developed a number of years ago by exida. It is documented in the paper Accurate Modeling of Shared Components in High Reliability Applications. You can either Google that name, or I've put on the slide a link where you can actually download this paper and give it a detailed read on your own if you would like for further information. But what we have happening here in this example is we have a steam turbine with a BPCS sensor. This is a shaft speed sensor, BPCS sensor. It's a shaft speed sensor going to the basic process control system, which is then using a positioner to adjust the control valve and regulate steam to the turbine to hit our target speed. Then we have a safety instrumented system that is also monitoring that shaft speed independently. Right there, let me circle the right one. Goes out to our safety logic solver, and in the event of high speed or overspeed, it will actually trip this on-off valve, but it has a secondary solenoid going to the control valve that will then override the BPCS and trip the control valve and close the line there. So similar to the example we looked at earlier, if this control valve fails open, and even if it's a fail closed valve, there is a potential that it could fail open. Then if it fails open, you get more steam to the turbine than is desired. We end up in an overspeed situation. So it's caused a demand on our SIF, and the SIF responds, but it's degraded because the control valve is not performing correctly, and we have only the on-off valve So we've got reduced reliability as well as a demand here. And I'm just kind of repeating this here on the next page, that we need to look at the shared device and understand how it affects both of those layers of protection for common cause. And one thing that we would note, if we went in and we ignored it as previously, if we ignore the common cause failure in our calculation, including data, we are going to end up with a number that is optimistically high, because we're looking at it from a perfect SIF. But if we then go in and look at only the dedicated SIS valve, this is going to be pessimistically low. So what we really want to do is make the adjustment where we account for that control valve failure in order to obtain a realistic RRF for the verification. So again, I'm showing this to you just graphically to restate what we are doing. We are going to calculate what we would have if we had a shared system with two valves and it was a perfect world. We had no common cause. We are going to look at what the RRF would be, or the PFD average would be on the conservative side if we had we're in just the degraded state and have just the SIF, and then we're going to make an adjustment between them that looks at this common cause failure. So our steps to do this are really pretty straightforward. The first thing we need to do is go back to our PHA, our LOPA, our SIL determination, wherever it was, we looked at what the overall initiating event was for overspeed scenarios. Get that initiating event from the frequency or from the LOPA. I went out and looked it up in the LOPA. In this case, we have a single initiating event, which gives us a 1e to the -1 or a 0.1 frequency of failure, which is very consistent with what we would see in most data references, such as the CCPS LOPA handbook would recommend for a failure of the valve, which is our initiating event. Then we need to look at what is the common cause failure. So we may have other things that could lead to an initiated event, but we also want to look at just what is the frequency at which the valve failure itself, the valve or the actuator failure only, as opposed to this overall initiating event, may well include things like an operator error that would drive the valve to the wrong position, or failure in a different part of the BPCS is included in the first one. In the second one, we are actually isolating just what is the valve and the actuator. Then we're going to go out and do the two calculations on our excellentia, where we look at the shared version, the overly optimistic one, or the degraded version, where it is the SIS valve only, the on-off valve only. We do our PFD calculations, including our beta in those, and get the risk reduction factors of 130 and 28. We're going to go out and build an event tree to calculate the overall frequency, take our basic shared version, and then we are going to add in essence, the failure that comes from our shared valve. And then we are going to calculate the risk reduction factor, which is simply the ratio of the hazard frequency when we do not have a SIS versus the hazard frequency with the SIS. And of course, when you're doing this, you want to make sure your documentation and the assumptions that go into the event tree all become part of your permanent documentation. So looking at this in detail, I've got our little steps here so we can reference them. So the first thing we want to do is our overall initiating event frequency, which we determined back from PHA or LOPA. Then we've got our calculation of the SIF if it has two valves in our final elements, the shared one. And we are using that to calculate an intermediate event frequency that is our base event. The bottom line is going to be our adjustment for the valve failure. So we calculated this common cause fraction, and now you can see I've shown you the equation, how we actually did that. We went out and looked up the actuator and the valve are the two components that are shared. So we went to literature and looked up the failure rate in fits, added those two together, that's what the second row is, and then converted it from fits to failures per year, which is where we got that 2e to the minus 2. From our other SIL verification we did in Excellentia, we have determined what the independent failure, what the degraded is, because once we have the initiating event of the valve failing, the control valve failing, that leaves us only the situation where we have our individual SIF to respond to it, and we calculate that intermediate frequency. Sum these two together to get our overall event frequency, and then we use our equation to ratio the event frequency with the SIS and the event frequency in a perfect world overall, and then the outcome frequency when we consider adding in this BPCS failure. So here's kind of a summary. We got a little summary table down here of what the numbers are on the 2 range and then where we ended up. And you will notice that this did not actually end up as a mathematical average. It's actually a little lower than what you would average those 2 numbers. So just in review, IEC 61511 does require that any source where we have common cause failure be demonstrated, and that our assessment needs to show, are they sufficiently low in comparison to overall safety integrity requirements. While our beta in our calculations does tend to address those independent ones, it does not adequately capture these dependent common cause failures, so you need to go through this extra step to address those. And we would recommend the quantitative approach because it does, over the qualitative, because it does offer you some consistency, and the methodology the paper shows that this methodology is appropriately conservative to provide always err on the side of caution. So that's kind of it for our topics. I'd just like to point out that, and I'll get to your questions after we run through the next couple slides, Exida Academy schedule. Exida is still doing all of our training. We've got a lot of online type training now, but here's our schedule for North America. If you are not in North America and would rather look at other venues, if you go to the exida.com training, you can look up the schedule in your region, and of course the online, that's when's convenient, right? We've got self-paced training available in a number of different areas, so you can always find that at the exida.com training online for our self-paced programs. And then keep up with the news. We post frequently on Twitter, Facebook, and LinkedIn. And of course, we like to hear from our customers. You guys run into real world problems. So if there's something that you'd like to see a webinar topic on, please send that request for a topic to academy@exida.com, and one of our many webinar hosts will pick that up and we'll do a webinar eventually. We're going to answer the questions that have been coming in here in just a minute, but if you have any follow-up questions and you want to contact me by email, my email is here on the screen. I also encourage you to look at the Exida website, because we have access to a lot of different references, books. You can go see old webinars here. We've got our white paper pages, additional other tools that are available that really do help out a lot. So I encourage you to join us there. All right, I'm going to go over here and look at the questions. How do you demonstrate common cause in a fault tree for a case where we have 3 SIS transmitters used in a SIF and an M out of 3 signal is passed to the BPCS for control? Actually, I would argue in this case, we've got our failure rate within the SIS, so we can look at the reliability in the SIS independently in its verification. But because you're passing a signal to the BPCS, if the SIS has failed, the BPCS has failed. So in that case, your probability of failure on demand, you've taken out 2 layers at a time. If there's just an error in that information, I would think, depending on how your process control works, if it's getting bad information to use for your control signal, and your SIS is using that same bad information to assess the trip conditions, then you may have a common cause that's approaching 1 there when you've got shared devices. But that would be a good topic to go in and look at as an example in a future webinar, maybe. How low is sufficiently low? I knew that was going to be a question someone was going to ask. Unfortunately, IEC 61511 is a performance-based standard. Therefore, it is subject to the interpretation of the users. So the idea of sufficiently low, that what I might decide is sufficiently low, others might think, well, that's not so different. So the examples we saw here today, there was quite a significant difference between the calculating the ideal world and taking into account the shared common cause. And that's why exida, we generally say it's not recommended to use that practice, because in my mind, 30, 40, 50% is significant, is incredibly significant. How low is sufficiently low? I mean, if you can show it is less than a beta, you may be able to make the argument, if it's less than 5 or 10%, you may be able to make the argument that that is sufficiently low. But it really comes up to the individual's confidence, or the risk tolerance, I think, of the organization to decide where that number is. But if the cause of the event is the FCV failure, the solution is wrong since the beginning. I'm not sure I understand that question. So if, I think maybe it didn't all come through or something. So if in any given system there is a possible common cause failure, then the SIF cannot be considered IPLs in a LOPA. You must do this analysis right. Generally, when I am facilitating a LOPA, I try and keep independence between the BPCS and the SIS. And granted, if you're doing project work, the design, you've got what's on the P&ID that you're doing your PHA on, and your LOPA is based on. And chances are it may show those things as independent, or someone may try later on in design to connect things up. So when I'm doing LOPAs, I always try and keep those just as independent as you possibly can, recognizing the standard does allow for some lack of independence there through this common cause, and we can actually incorporate into the LOPA a common cause factor, and that's maybe another webinar that we ought to look at in the future, how to do this from the LOPA perspective. How do you account alarm and operator action in an independent transmitter that goes to the BPCS if the cause of the event is the failure of the BPCS loop, if they have different instruments but the same BPCS? Would you take the instrument with the alarm to the SIS? If yes, would you have to add a SIF? The alarms will be in the SIS and also in the SIF. There's really several questions kind of buried down in that. IEC 61511 does allow up to 2 layer credits within your BPCS, but often one of those layer credits is the device that fails. So if you have a failed, you're limited to just 1 protection layer. If you choose that to be your alarm layer, then you've already consumed that in building up your basic process control IPL. Sending the signals from your BPCS to your SIF, for the SIF to act on, is actually counter to what is permitted in the design. If the SIS is using any data from the field, it has to come into the SIS first, and then it can share it with the BPCS. So there's a couple places where we can take some issues with that. Okay. If you assess the demand caused by failure of the shared valve as a separate PHA LOPA hazard scenario, and the single valve RRF meets TIL, is the extra event tree still needed? I suppose on a theoretical perspective that if we can evaluate it out in the If we can look at that consequence in our LOPA, then what that's going to do is adjust our SIL target. We don't want to account for it both in the LOPA and in the verification. This particular webinar was really looking at it from the verification perspective. I think mathematically you probably could address it by adjusting your risk reduction factor to compensate, or your SIL target to compensate it, basically increasing your risk reduction factor. But the issue with doing that, I think, at the LOPA stage is you're anticipating what the design is going to look like or what's going to be used in the design. So there may be some iterations involved. I would prefer to be kind of a purist in the LOPA and keep things as separate as possible. And then as the design evolves and we get into the verification and validation stage, make sure we've adjusted all of this criteria. So we've got a little smaller group this afternoon, so we had some fewer questions. I think I have, I've gone through everything that's here on the list. So I'll give it a second if anybody else has any follow-up questions. Again, I'd like to invite you to send me an email offline if you think of something afterwards, and to definitely peruse some of our reference material on exida, the books, the white papers, the other resources and tools that are available to you. All right, so if we have no further questions, we're going to go ahead and end this. Thank you so very much for spending your time coming to join me today. And again, if you have any questions afterwards you want to follow up, please, I invite you to contact me at dchastain@exida.com. Oh, 2 more just came in. Let's do these real quick. Will this be added to the recorded list so we can watch it again? Absolutely. With every one of these webinars, you'll be sent out a link to where it's posted on the recording, and then also a link where you can get a copy of the slides. Please plan another webinar on the M003. I will make a note of that to get that in our list. And where do we get the copies? Okay, so like I said, you'll be getting a email follow-up on this that's going to give you access to where the webinar is posted and where the PowerPoint presentation or the copies, a PDF of the slides will be available to you. That probably will be in your inbox sometime tomorrow. All right, again, thank you very much for attending, and everybody have a wonderful day. Bye-bye.